What we're going to do here is solve for x in equilibrium problems after we have gotten through building our ICE table and put the equilibrium concentrations into the equilibrium constant expression. There are basically 5 ways that we'll do it. This is other than putting it into an equation solver function on a calculator. One is, we'll check first whether it could be solved by taking the square root of both sides. This, of course, would be the easiest, but it won't always work. Second, we could make the approximation that any plus or minus terms are negligible compared to the number they're added to or subtracted from. We could shift first the equilibrium to the favored side before doing the ICE table. We call this the if-ICE method. The favored side would be determined by what the size of the k value is in the equilibrium constant expression. The k, if it's very small, would mean that the reactants are favored. If it's very large, the products are favored. After we create our new ICE table, we would then assume that the plus or minus terms are negligible, as we did above. Now, what if these simplifications don't work? Well, then we're stuck with solving via the quadratic formula or solving via successive approximations. Here's an example. I've written the equilibrium constant expression that we got after going through the ICE table. This has the equilibrium concentrations in it already in terms of x. Now check whether we could solve this by taking square root of both sides. Yes, we could. On the right side we have x squared on the top and 25 minus 2x all squared on the bottom, so yay! Solving gives 0.48, and this works. Let's try it again a different way. We'll try the second method, where we make the approximation that any plus or minus terms are negligible compared to the number they're being added to or subtracted from. Here we have a 2x being subtracted from 25. Now what if x turned out to be something like 0.1? If you had 2 times 0.1, that would be 0.2. Subtracting 0.2 from 25 with no decimal places would give an answer of 25. Two significant figures, the proper number. So pretty much you've got the same answer whether the 2x was there or not. So we're going to assume the 2x is 0 and solve the problem that way. We have x squared over 25 squared now, and you can solve that for x. It comes out 0.5. We always must check in this method that the error that we are creating by making this assumption is no more than 5%. We check that by saying the x is 0.5 times the 2, because we had a 25 minus 2x, divided by 25, that's the number it was subtracted from, times 100 for percent, gives us a 4% error. That's under 5%, so it's okay. So this works too. Suppose we wanted a more accurate answer. We have just done making the approximation that the plus or minus terms are negligible compared to the number they're added to or subtracted from. We got the answer before of 0.5. Now we're going to solve via successive approximations using that 0.5. We substitute 0.5 into our original equation here for x in the subtraction term. So 0.5 times 2 is 1, 25 minus 1 is 24, so we have the equation as shown here. Solving that gives us 0.48. Then we do it again. Substitute 0.48 in for x in that subtraction term. 2 times 0.48 is 0.96. 25 minus 0.96 is 24.04. So we have the equation as shown here. We can solve that and we get 0.48. Guess what? 0.48 is the answer. So we see that once we've gotten the same answer twice, we have solved the problem. Let's move to another problem. This one looks much worse. If we check to see whether we could take the square root of both sides, we're in trouble. You can't possibly just do that in a simple way on the right side. So let's try making the approximation that any plus or minus x terms are negligible compared to the number they're added to or subtracted from. In other words, we'll make all the minus 2x, plus 2x, and plus x terms 0. Well, that doesn't help because there's no x left to solve for now. So, what about shifting to the favored side before doing the ICE table? The equilibrium constant here is small, so which side is the favored side? Right? Reactants. Okay, so we'll do that. Now I haven't shown you the original reaction equation nor the ICE table here, but let's assume we can do that. We'll shift it to the reactant side and then create a new ICE table. Then we will assume that the plus or minus terms are negligible. We do the first part of it, shifting the equilibrium, put in the new ICE table. The K after shifting the equilibrium and creating the new ICE table, the expression for K is as shown here. Now I didn't show you where this came from, but just let's grant me that this is what it is. We'll look at this and then take the minus 2x and the minus x and assume that they are 0, very small. When we do that, we solve the problem. We get 0.00536. Remember that after we get an answer, making this assumption, we always have to check to see if the error is no more than 5%. So how do we do that? You're going to take the answer for x, 0.00536, times 2, because the term here that has the most error caused by ignoring the x is the one that has the times 2. That's the 0.5300 minus 2x term. So we'll take the 0.0053x times 538.6 rather times 2, divide by 0.5300, then times 100 to make the percent. So that's a 2% error. That's okay. So have we done it? Yes, we have. If we wanted to do a more accurate answer, what could we do now? We could do more successive approximations and plug our answer here back into the original equation, getting a new answer until we get the same answer more than once. We don't have to do that because a 2% error is acceptable, but you could do that if you want.